Hey guys, welcome to this video on kinetic friction. This is a continuation from the video on static friction, so if you haven't checked that one out yet, you want to go back and check that one out so that this one makes a lot more sense. As always, I encourage you to play back the video at a faster speed if you're just trying to get the general basics, because I record a little bit slower just to make it easier to explain, but watching it at a higher playback speed may be more appropriate for what you're trying to achieve. So what we're looking at here is the relationship between kinetic friction and normal force. And what we want to do here is the same basic thing we did in the previous video. We want to vary the contact force between the two surfaces, which is the normal force. And we want to see how the amount of frictional force changes based on the contact. Now it makes sense, as I described in the static friction video, it makes sense that if you have a greater contact force, so if the two surfaces are pushing harder together, there's going to be more friction. And we want to find out what that relationship is. So I've already sketched the two different scenarios on here, but let's just take a look at how the data was collected. So I get this little motion man here and I push, and I see that we're looking at kinetic friction, so I'm looking at this. No matter how much harder he pushes once it starts to move, the kinetic frictional force is constant. It's not changing. It stayed at 94 newtons. So I'm going to draw a free body diagram over here where I have the force weight of this crate that's on the screen, and then I have the normal force. He's pushing with an applied force that for the majority of the time, or for actually all the time, is greater than the frictional force until he's not pushing anymore. And this is particularly kinetic frictional force. So this is much greater than this, but these two are even. So if I write out my net force statement here for the vertical dimension, I have that the normal force minus the force weight is equal to 0. This means that the normal force is the same thing as the force weight. But just remember, we're always finding the relationship truly between the normal force and the frictional force. Now, how do I vary the normal force? Well, if I put another object on top of this, I've now increased the normal force between, or the normal force of the ground pushing up on the crates. So this contact now has increased between the two. Now that would imply that the frictional force increased, and we can see that it did. So if I take this off again, you see that the frictional force required changes. Now obviously there's not friction acting right now because nothing's moving. There is no horizontal force in either direction. It's just the simulation showing the change. But I can see that anytime the normal force increases, the amount of frictional force is going to increase as well. And I did that with a variety of different combinations of objects here. And what I found was that I got a line that looked like this one. Okay, so this is what I'm going to call here, for lack of a better term, middle friction. And the reason I'm calling it middle friction is because I have this little slider set in the middle right here. Now I'm going to reset this simulation. I'm going to try do it again, but I'm going to add lots of friction. So basically what's happening, if you look at the surface, is the friction is becoming, or the surface is becoming rougher as I slide this up. Now let's take a look and see here what's going to happen. If he starts to push, we now see that there is a greater amount of friction even though I have the same normal force. So if I kept track of the normal force over here, let's say this was when I had 50 kilograms, so that's going to be 500 newtons, okay? And then let's say I did it at 1,000, I'm just making up some values here, and then 1,500, and then 2,000. What we see is that with the same normal force, let's just draw a little line there, we have two different frictional force values depending on what the amount of friction between the ground is. So in other words, an object that has contact with the ground of 2,000 newtons is not the only factor that affects the amount of friction required or experienced. You can see here that at the exact same normal force, I'm going to have two vastly different friction values here and here. And it turns out that the slope of each of these lines represents that term again that came up in the last video, which is the coefficient of friction. And in this case, it's going to be the coefficient of kinetic friction. Now, coefficient of kinetic friction, again, is going to be symbolized with the Greek letter mu, which to some people, again, looks like a cursive M or a U with a tail on the front. So we combine M and U and make the word mu, but it's actually a Greek letter. This is going to have a little k next to it now because it's kinetic, coefficient of kinetic friction. And this, as we found in the last video, is a unitless number. And you can see that from how we collected the data on the graph here. Newtons divided by newtons just gives us 1. So the units cancel. It's a unitless number that describes, and this is not the most scientific definition, but it describes the roughness or smoothness of a surface. Now, really what it is a ratio of the force of friction to the normal force for a particular surface. So it's telling you the amount of kinetic frictional force that you have per amount of contact force, and that gives you the mu value. But it describes the roughness of the surface because it describes the fact that for the same normal force, you will end up having more friction if your surface is rougher. So the bigger the number, the bigger the slope, the bigger the number of mu, which is the same thing here, the more rough or the rougher the surface is. So again, the coefficient of kinetic friction describes the surface contact. It's different than the actual amount of friction because the amount of friction is not only dependent upon the roughness of the surface, it's also dependent on how tightly the surfaces are pushed together, also known as the normal force. So when we write our final equation here, what we're going to have is the force of kinetic friction equals the coefficient of kinetic friction times the normal force. This is just a linear equation, right, where y is the force of kinetic friction, the slope is mu, and x is the normal force. So this equation is going to become very useful for us in a lot of different situations that we can use to calculate various things about friction. Now the last thing that I want to do in this video is compare the static friction with the kinetic friction and see which one is bigger, if either, and why that might be so. So here I have a graph of the frictional force, and this is generic frictional force, so it's going to be kinetic and or static, and I'll show you why that is in a second. And here's going to be my force applied. So I want to make just a comparison between these two. So what starts to happen here, let's see, when I start to push the box, notice how the static friction, which is right now the kind of friction because nothing's moving, the static friction is increasing as I push. And we saw that in the last example. Now when I hit a certain value, we see something change drastically. Let's put the slider back in the middle here. In fact, let's just set these back up again. I start to push. The static frictional force is increasing, 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 increasing. I hit a breaking point, as we saw there. The maximum static friction looks like it was maybe 120 something, and then it drops all the way down to 94. So what we would see on our graph here is that the static friction increases, increases, increases. We hit this maximum value, then the frictional force changes to kinetic friction. It drops back down, and then we see that the kinetic friction stays constant the whole time. So if we were going to label our graph here, we would label this portion over here the static friction. We would then hit our peak, which is the maximum static friction, and then all of a sudden we have this drop off, and then it becomes kinetic friction. So what we see happening here is that there's a static friction portion, before the object starts moving. So what I might want to put here is this is when the object is at rest. Okay, rest is going to describe equilibrium. Okay, and so this means that all the forces would be balanced, right? They're slowly increasing as the guy pushes. We hit our maximum value, and then it changes into kinetic friction. And during kinetic friction, there's a variety of possibilities. It could be moving at a constant velocity. It could be accelerating. And remember, accelerating could mean also decelerating, slowing down or speeding up. And so you want to make sure that you consider both. So if we think about what's happening here and we look at this little guy pushing, at some point I hit this 94. Now what I could do is decrease my force back down to 94 and I'd be moving at a constant velocity. It's hard to get it to be exactly right, but there you see it's moving at a constant velocity. I could push harder, it will start to accelerate, but the frictional force is not changing. So you can see that there really isn't a relationship between the kinetic frictional force and the applied force because there's a flat line. It doesn't change after I've hit the maximum value. So let's write in the little equations here to wrap this video up that we can use to calculate. On the kinetic friction point, we're going to have the force of kinetic friction is going to be equal to the coefficient of kinetic friction times normal force. The maximum static friction, I'm just leaving out the other F here just to save us some room, is the coefficient of static friction, which is a different number, times the normal force. And this is all the same normal force here for this particular example. And in this case over here, it's not really an inequality, it's going to be an inequality because we have things that are changing. So I'm going to have the coefficient of static friction times the normal force, and then I'm going to have the force of static friction. And in this part over here, I'm going to have some value that is going to be different. So it's either going to be less than or equal to this particular value over here. Now the equal to part, of course, comes in over here, so I'm going to actually erase that part just to show that the static friction will be less than these. Then I'll hit the maximum value, then it will drop down to this. So make sure that that all makes sense to you, and then try out some practice problems. And again, I have a link to the simulation in the description below.